In an interview with Michael Bernard, Paul Martin detailed the reasons why things were uncompetitive, lower on the Liebreich ladder, by explaining the physical properties that made them not work. You can see here the Liebreich ladder in the middle, and around it, the rungs of the ladder B through G. I found no reason to put up the A rung because there's really unavoidable. I'm going to focus on one of the elements so you get the idea of what Paul Martin was doing. This is long-haul aviation, and this is storage shape. When a plane flies, it has to push its fuel through the air along with everything else that is in the plane. And the engineers found that they could store the fuel in the wing, which has the airfoil shape, and the fuel could be carried economically and physically in a way that works. But hydrogen can't be stored in a wing shape. It's either a gas, where it has to be stored under several atmospheres of pressure, enough pressure such that either a very heavy cylindrical tank needs to be used, or a light aluminum tank wrapped in carbon fiber so that it won't blow itself apart. If it's a liquid, it has to be stored at nearly 0 degrees Kelvin, absolute zero, minus 400 and something degrees Fahrenheit. And what it takes to keep that cool is just not worth trying to fly through the air. You'll have a lot fewer passengers on any given plane. So you can't put a cylinder shape in the wing without changing the airfoil and the effectiveness of flying. So for that, among other reasons, and there's others listed here in the reasoning, you can see in the stack bar, there's a series of things that mount up to pretty high penalties for trying to use hydrogen in a plane. It makes this particular application of hydrogen not viable. And there are many other examples here, and you can see the stack bars here, each of which correspond with one of the little lozenges in the Liebreich ladder.